This video will be on section 4.1, critical points, function direction, and extrema. So first we'll talk about critical values of a function and what they are, why they're going to be important. We'll see that they're related to figuring out where a function is increasing and decreasing, which you should be a little familiar with as far as if you're given a graph, but we'll review that very briefly. And then the last little section, also built on the previous sections, how we find local maximums and minimums. Maximums and minimums are referred to as extrema. So really the whole goal of this entire chapter is to be able to do word problems in 4.6 that will ask for the maximum or minimum of a function. And the reason why this is so important is when you're talking about business applications, you want to maximize things like the profit and the revenue. You would like to minimize things like the cost and so on. And typically you can't just plug in very messy formulas into a computer and or a calculator or a computer and graph it and expect to figure it out that way. So we're going to develop how to do that using our calculus. So until now, really, you know the maximum or minimum of a parabola, which corresponds to the y value of a vertex, but we want to be able to do it with any function within reason. All right, so just as a reminder, I'll remind you on the calculator, a parabola, that's y equals x squared. And if you graph that in the standard window, the vertex here is a minimum. And we would say there's a minimum of 0 since the y value is 0 there. Now if we do negative x squared, this is one that will give us a maximum because our vertex, it opens down and the vertex appears at the top. Same minimum value as the other maximum value, or they're both 0. But one thing, I'll leave these up here when we refer back to them, because when we're dealing with problems in this section, in this chapter, you're going to want to have this picture in your head a lot, even if we're not dealing with parabolas specifically. All right, but we'll start by what is a critical number. All right, so a critical number, C, of a differentiable function, f, so that just means we can take the derivative, is a number such that C is in the domain of f. So this is highlighted because there will be a subtle difference between another idea right below. It must be in the domain of your original function, and either the derivative is 0 or undefined at that value. All right, so really, I'll highlight these 2 points here. First, we want to figure out where the derivative is 0 or does not exist. So typically I like to think about, if the derivative formula is a fraction. Now if it's not a fraction, then we just set it equal to 0. Well, what you do to find out the critical numbers is set the top equal to 0, set the bottom equal to 0, and solve. Right, because what this will do is when you set the top equal to 0, this will give you when the derivative is 0. And when you set the bottom equal to 0 and solve that, it will tell you when the derivative is undefined. Or does not exist. So when you do that, you'll actually find all of the partition numbers. So what the partition numbers are, so we will end up making number lines using these critical numbers to figure things out. However, Any number not in the domain of f will also be included, in addition to the critical numbers. So when you do this, you're going to get the partition numbers, and then you have to make sure the numbers are in the domain or not. But when we deal with partition numbers, we don't have to worry about that. We just include both from here. So the critical numbers we need to check if they are in the domain, which we'll see with one of our examples throughout this section. All right, so it says for each of the following functions, f of x, find the derivative, the partition numbers, and the critical numbers of f. All right, this kind of guides you along the process. You have to find the derivative in order to find the partition numbers, and you have to find the partition numbers to find the critical numbers. Right, so we'll just do that in order and kind of talk about it as we go along. So the derivative, nothing special here. The derivative of x cubed is 3x squared. The derivative of 27x is 27. And the derivative of 8 is 0. So that's our derivative. Now to get the partition numbers, since there's no denominator, we just set it equal to 0 and solve. We do 3x squared minus 27, our derivative, set it equal to 0, and solve this. Now we can solve this one we just have an x squared there, so we don't have to worry about factoring. We can add the 27 to each side. We get 3x squared equals 27. Now we divide each side by 3 to get x squared by itself. We get x squared equals 9. And then to go from x squared to x, we do the square root of each side. Don't forget the plus and minus when we do the square root. And we get x equals positive 3 and negative 3. These are the partition numbers. Now what we do to go from here to get the critical numbers from the partition numbers is we check and see which one of these are in the domain. The ones that are, we keep. The ones that aren't, we throw away. So which partition numbers are in the domain? But this is important. It's the domain of the original function. So we're going to use this one here. We're not using the derivative. But this one is actually pretty straightforward because the domain of any polynomial is all real numbers, right? But you can also check by plugging in. If you plug in 3, do you get out a real number? If you plug in negative 3, do you get out a real number? Right, remember the way we check the domain of most of our functions. If we have a fraction, set the denominator equal to 0, throw those numbers away. If you have an even root radical, the inside must be not negative. And then we also deal with the log functions. The inside of a log must be positive. Right, but since our domain is all real numbers, what that means is that negative 3 and negative 3 are both critical numbers as well. So they're both in the domain, which means they are both critical numbers. Right, if, for example, 3 wasn't in the domain, then we would only include negative 3. It's possible that every partition number is not a critical number. And you see here, it's possible they all are. All right, but we'll build on this example as we go through the section. All right, so number 2, we want the derivative We want the critical numbers, or partition numbers, and then we want the critical numbers. So I want the derivative first. Let me rewrite the directions just because it's a few steps. So we want to define the derivative, partition numbers of our derivative, and then critical numbers of our function. All right, so to do the derivative here, there's two ways to do it. I'm going to do it the way that I prefer, which is, since there's just a 1 up here, if I bring the x plus 7 up to the top, this becomes x plus 7 to the negative 1 power. You can also use the quotient rule here. This is one of those rare examples where it's actually easier to do something else. But you can also use the quotient rule. It's totally up to you. All right, so I'm going to do the derivative of x plus 7 to the negative 1. All right, this is something we would start with the power rule. So bring our power down, negative 1. We rewrite the inside. We subtract 1 from the power, negative 1 minus 1 is negative 2. And then we multiply by the derivative of the inside, the chain rule, because it's not just x, but the derivative of x plus 7 is just 1. Because it might have been a while since you've done the chain rule, I'll just write a little comment here. The 1 is from the chain rule, even though it doesn't affect our answer. You don't want to forget that if it was 2x plus 7, then you would have a number there to affect your answer. But when it comes to critical numbers and partition numbers, keep thinking about what we're going to do. When we're going to have a fraction, we set the top and bottom equal to 0 and solve. Whenever you deal with negative exponents, it's not obvious how to solve it unless if you make exponents positive. So I'm going to make this exponent positive by bringing it back down. So I got a negative 1 on top times 1 doesn't change it. And then the x plus 7, I'm going to square that because I'm changing the exponent back to positive. If you do the quotient rule, you actually get this out right away, but of course the quotient rule takes a few steps. So it's up to you which way you do it. So we'll just write a comment. When finding critical or partition numbers, never keep negative exponents. That'll lead you down the wrong way 99% of the time. Okay, but this is our simplified derivative. Right, and we kind of mentioned before, but whenever you have something to a power, that really is simplified. So here what are the partition numbers? Well, we take our fraction, set the top equal to 0. Well, the top is just negative 1, so negative 1 equal to 0 gives us nothing because negative 1 does not equal 0. And we also set the bottom equal to 0. And the bottom is x plus 7 squared. And we want to solve this. And this one has an exit, so we got to do it. It's not going to be nothing. Do the square root of each side to knock off the squared. Now we do always have to do the plus or minus when we do the square root, but square root of 0 is 0. Plus or minus 0 is just 0. It's the same thing. So we've got just x plus 7. The squared and the square root knock each other out, equals 0. Subtract by 7 and we get x equals negative 7. This is the partition number. We only have 1 for this function. That's all right. You might even have 0 sometimes. right? And then remember the last thing, the critical numbers come from the partition numbers. Now that we only have one value, -7, we ask, is -7 in the domain of f, our original function? And you can answer that a couple ways. You can figure out the domain at the beginning and just see if it fits in there or not, like we did with the previous one. Another way you can figure it out is just plug it in and see what happens. So I'm going to show you the other way with this one. We get f of -7 equals 1. I'm going to use the original here because once again, dealing with negative exponents can be deceiving. And we got -7 plus 7 on the bottom. -7 plus 7 is 0, and dividing by 0 is bad. This is not in the domain. Right, -7 not in the domain. What that means is there are no critical numbers for this function. The only possible one we have is -7, and it's not really 1. So there are no critical numbers for this function. And that's okay too. Right, but as we go through the rest of the steps in this section, because the ultimate goal of all these problems is to figure out with the function, what are the critical numbers, what are the partition numbers, where is the function increasing or decreasing, and then finally, where are all the maximums and minimums. Right, so the second step to that process is figuring out where the intervals of increase are increasing and decreasing. All right, so the partition numbers of your derivative, for the previous one, -7, for the first one, 3 and -3. The partition numbers are what we use to determine the intervals on which a function is increasing or decreasing. Right? The reason why we don't actually use the critical numbers is because numbers that are not in the domain of a function are also where you can change increasing and decreasing. Right? And to kind of explain why, why is it so important to figure out these partition numbers? Well, we can just look at the example, what happens when the derivative is 0? Right? Kind of mimics this first one here, but I will go back to the parabola. Right? And let's just only do one of these graphs. So the graph of y equals x squared looks this. We acknowledge that we have a minimum at the vertex at 0. And you'll also notice it goes from decreasing to increasing. So it switches there. Well, what's the derivative at 0? You can work it out pretty quickly. Do the derivative of x squared, which is 2x. If you set it equal to 0 and solve it, you get x equals 0. And that's exactly what it's telling us. When the derivative is 0, it's going to tell you when the graph might change from increasing to decreasing. But also if the derivative does not exist, it can do the same thing. But those are a little more complicated to see. So we recall that a function is increasing if the derivative is 0 and decreasing if it's negative. Right? We dealt with that with word problems, interpreting word problems. And we solve the inequalities that are going to pop up by finding the partition numbers of our function derivative, make a number line, and then solve inequalities like we did previously in the class. All right, now I already mentioned kind of a picture, but just to draw and have something in the notes here. If our function looked like this, And we wanted to, just from this picture, know where it's increasing and decreasing. So let me draw this side out a little bit more. Then it's increasing when it's moving up as we move to the right. So over here on the left, it's increasing up until we get to the top. And then anytime you have a what looks like a maximum or minimum, right, the top of the hill, bottom of the valley, it's going to switch. So now after it's increasing, it starts decreasing. And it's decreasing on down till we get to the bottom. So it's decreasing here. And then it's moving, for decreasing, it's moving down as we move to the right. Right, so anytime you want to look at a graph and know whether it's increasing or decreasing, you have to read it from left to right. And then after we get to the bottom here, it starts moving back up. Since it's moving back up, it is increasing again. I won't annotate it like last time, but it's doing the same thing. And once it gets to the top, it's kind of where I stopped drawing the graph. But if it moved back down, it'll be decreasing. All right, now one thing that's important about finding intervals where it's increasing or decreasing, which will work out in our problems. If I call this back here, like let's say it starts at A, and this is number B where it switches, and then number C where it switches, and then number D at the end. When you write the intervals of increasing or decreasing, you always use parentheses. You never include where it changes or where it stops. So increasing or decreasing intervals only use parentheses. But this will make sense when we solve the inequalities because we're going to solve greater than or less than, no equal to part. But just to kind of elaborate on this example, if we wanted to write the intervals where it's increasing, it would be parentheses from A to B, and then comma or union, whatever the homework says to use, and then from C to D, but all parentheses. And then it's decreasing from B to C. Once again, both with parentheses. If you ever use brackets on these, even if you just use one by mistake, it's wrong. You have to use parentheses. B and C are where we have a maximum and minimum of these graphs, and that's why it's not increasing or decreasing. And we just never include endpoints. So the graph here stopping at D, starting at A, we never include endpoints. Right, but now we'll take the two problems that we had before and figure out where they are increasing and decreasing by making what's called a sign chart. And we did this previously in the class, but it's been a while, so we'll definitely remind you. So for the following functions, we want to know where the graph is increasing or decreasing. The information you need to do this, you need the derivatives, the first derivative. So the derivative of this, we can just recompute it real quickly. It's 3x squared minus 27. The other thing you need are the partition numbers. Since we already did that, we won't redo that again, but the partition numbers we got here were -3 and 3. Okay. So here's how we make the sign chart properly. Make your number line. What you want to do is mark off all the partition numbers here. So -3 and 3. Now, it's actually pretty nice in that you don't actually have to solve the inequality to figure out where it's increasing or decreasing. We just plug in numbers in each interval and see whether it's positive or negative. So next, plug in a test value to f prime of x, the derivative, for each interval. Right, because we want to know where it's increasing or decreasing. We don't care if the function is positive. We care if the derivative is positive or negative. So I'm going to do -4. It's 1 to the left, -3. I'm going to do 0 because I always like to do 0 if I can, between -3 and 3. Then I'm going to do 4 to the right of 3. So I want to figure out f prime of -4, f prime of 0, and f prime of 4. All right, let's go ahead and do that. Our function derivative is right here. That's why we need that to do this part. We plug in -4. What do we get? -4 squared is 16 times 3 is 48. 48 minus 27 is 21. But what's important about here, it's not the number specifically, it's the fact that the number is positive. So what I do is I put a plus sign since we got a positive number. And I just do plus and then minus and plus just wherever, whatever they turn out to be. All right, so f prime of 0, the next one we want to plug in. We want to plug in 0 to our derivative, and that one, it's always nice to plug in 0 because it's usually pretty easy, and that gives us -27, but that is negative, so we put a minus. And then finally, plug in 4. 3 times 4 squared minus 27, and that's going to be the same thing as up here, because 4 squared is 16 times 3 is 48. 48 minus 27 is 21. Once again, if you plug these numbers into the original one, they might sometimes match up, but very rarely. It has nothing to do with what sign the derivative is. You got to make sure you do this. All right, so what is this telling us about our function? Well, where it's positive derivative means it's increasing on this interval. So -infinity up to -3 is where it's increasing. It's all, excuse me, it's also increasing from 3 to infinity because 4 is inside that interval. And it's decreasing between -3 and 3. All right, now if you remember, just the one thing to remember here is that the intervals, we don't use the endpoints. So when we answer this, because that's really what we want, is we want where it's increasing and decreasing. The decreasing interval is from -3 to 3 with parentheses, and it's increasing from -infinity to -3. Right, make sure you're using the partition numbers. And then it's also increasing from 3 to infinity. Right? That's what this part of this question is asking. So this is really the only thing we want to answer with. But in one problem, you'll probably more so see find the derivative, find the partition numbers and critical numbers, find the intervals where it's increasing and decreasing, and then the last thing we'll do, where do we have maximums or minimums? But we'll see after we made the sign chart, that part will be pretty short and straightforward. Right. All right, so number two, we want to do the same things. We want to figure out where the function's increasing and decreasing. We want to make a sign chart for the derivative like we did over here. And we need the same information because we're going to plug in numbers into the derivative. And then we're going to make our number line with the partition numbers. All right, so f prime of x. The derivative was -1 over x plus 7 squared. We already did that from above. And the partition numbers, we had 1 here, which was -7. Right, but we're going to follow the same exact guidelines. It doesn't matter, that both of these were critical numbers. And if you remember, -7 wasn't actually a critical number for this problem. You follow the same guidelines. It doesn't matter that there's a fraction or anything like that. So only having one partition number makes it a little bit easier, because the next step, we want to plug in a test value in each interval. Right, so just pick two numbers, one to the left of -7, -8, and one to the right of 7, which, like I always say, if you can plug in 0, it's the best thing to do. And we want to plug them into our derivative. All right, our derivative formula is right here. We got -1 over x is -8 plus 7 squared. And then simplify this. We got -1 on top, and on the bottom, -8 plus 7 is -1. If we square that, we get 1. So we get -1. All right, so what's happening at -8? We have a negative number, so it's decreasing, which I'll write in afterwards. And then when we plug in 0, we got -1 over 0 plus 7 squared into the derivative. 7 squared is 49. And -1 over 49, which is also negative. It's also decreasing. I used red, so let me do the same thing here. So it's decreasing to the left of -7. It's also decreasing to the right of -7. Now the question might arise, well, if we're decreasing on the whole thing like this, wouldn't we just write from -infinity to infinity? The answer to that is no, because it's not decreasing at -7. So for decreasing the intervals, we got -infinity to -7 and 7 to infinity. Right, it's not decreasing at -7. And then for increasing, it's not increasing anywhere. So that's also possible with our function. Right, so we've done most of the work for any problem in this section. Once you figure out where it's increasing and decreasing, the last thing to do is figure out where do you have maximums and minimums. Right, now to make the number line, we use the partition numbers. To figure out the maximum minimums, though, you must use the critical numbers, and we'll explain that with our two examples here as well. So to figure out maximum and minimums, we say, let's say C be a critical number, so it's in the domain of your function f. We say that f of C is a local maximum. This is the easiest way to word it when we have the sign chart. If it is increasing to the left and decreasing to the right, we say it has a local minimum if it is decreasing to the left and increasing to the right. And if it's not changing sign, so if it's increasing or decreasing to decreasing, it is neither. Right, but this preliminary step is the most important. If you're dealing with a partition number that's not a critical number, it can't be any of these. It's not going to be a maximum or minimum. So none of these apply. So double important reminder. Maximum minimums occur at critical numbers, not partition numbers. Right, so like with the first one we did, if you remember, the first one here, the partition numbers were all critical numbers, so there's not really a difference, but the second one here, there was a difference. So we'll talk about that when we get there. All right, so to understand where this is coming from, I'll draw a picture for each situation. Say we want to look at what a maximum looks like, a minimum looks like, and neither on a graph. This is the way I actually do it just with the number line, the sign chart that you make. And I find this most helpful because you'll see once we made this, the number lines here, it's just a matter of drawing in one extra thing. You don't even really need to memorize this. It'll tell you. All right, so at each one of these, we got numbers C. All right, so for the maximum, it says if it's increasing to the left and decreasing to the right. Well, if it's increasing over here, what I like to do is I like to draw what that means as the graph. We don't know the specific shape, but we know increasing means as we move to the right, it's going up. So it looks something like this. Right, it doesn't need to be a line. It's probably not going to be a line if you look at the actual graph, but it's just following that shape. And then if it's decreasing to the right, that means as we move to the right, it's going down. So it looks like a downward line. And what's happening right here at the top is we're at the top. Or sorry, what's happening right here at C is we're at the top. So it's at a maximum. Right, so if you're switching from increasing to decreasing, it's going to be a maximum as long as you've got a critical number. Minimum, you do it the same way. If we're decreasing to the left, which means it's going down as we move to the right, and then to the right, it's increasing, which means we move up as we move to the right, then you're at the bottom of the valley and you're at the minimum. Right, but if it doesn't switch signs, meaning it's just decreasing to decreasing or increasing to increasing, I'll draw the decreasing one first. It sort of looks like this, and then it's going down some more. So what this is saying is that your graph's going down, and then you get to this number and it's still going down. So it can't be a maximum or minimum. And similar for increasing. If it's going up and then you get to your critical number and then it's still going up, it's not a maximum or a minimum because it's just going up and up and up and up. Right. So it's pretty nice to just kind of remember if you draw this on your number line, then it'll tell you, and you don't need to really remember this in words. What you need to remember is that it must be a critical number. All right, but just to finish it up, we'll deal with our two examples again. It says find all local extrema, so we want to find all local max and mins of our two functions. So the information we don't need the derivative anymore. We need the critical numbers, which we've already found, because they must be critical numbers where they happen. And once again, write the critical numbers down for this part. Do not write the partition numbers because you might get something that's not really there. And then the other thing is we need the sign chart that we made from before, from the increasing and decreasing intervals. But when you're working a problem like this, it wouldn't be separated into each section. You just do the whole thing at once and you have it right there with you. All right, so the critical numbers from this one, I'll remind you, are -3 and 3. And then the sign chart You probably still have it in your notes. You can just refer back to it. I'm going to redraw it so it's right here. We mark off our critical numbers. And it was plus minus plus, which we wrote in increasing on the outsides and decreasing on the inside. But if you just draw this out, then it works out pretty well. So it's increasing over here, which means it's going up as we move to the right. It's also increasing from 3 to the right, so it looks like this. And then it's decreasing, so it's moving down as we move to the right in between. So what's happening at -3? Well, it's up here at a maximum. And what's happening here at 3? Well, since it's down here at the bottom and it's going to flip back up, it's the minimum at 3. Now with maximum and minimum, sometimes you're asked for only the x value, sometimes you're asked for only the y value, sometimes you're asked for both. So if you want the coordinate pairs of maximum and minimum, well, you have kind of two choices of functions to plug in, right? You can plug -3 into the original or the derivative. Which one's the correct one? Well, since it's on the actual graph, we're looking at the actual graph, we're going to plug it into the original. Okay, so for -3, plug in -3. We got -3 squared, or cubed, not squared, minus 27 times -3 plus 8. And let's see what that gives us. $62. So we have a maximum, right? That was a maximum of the y value of 62 at x equals -3. Or you might write as the coordinate pair -3 comma 62, just depends what the question wants. I'll do the minimum in a different color. So the minimum at x equals 3, we plug in 3 for x into the original. I don't know why I keep writing squared. So we got 3 cubed minus 27 times 3 plus 8. And go back to our calculator or do that by hand, it doesn't matter. I'm going to just do it in the calculator real quick. We get -46. So we have a minimum of -46 at x equals 3. Now, if you wanted to graph this, imagine graphing this and trying to find the maximum and minimum with your calculator is you'd have to zoom out quite a bit. You'd have to figure out, the y values aren't between -10 and 10 like our standard range. But what I'm going to do just so you can really understand everything we've done here is graph it. We got x raised to the 3rd power. Let's get rid of that squared. Let's just clear it. So we got x raised to the 3rd power minus 27x plus 8. Since we know where our maximum minimums are, what I'm going to do is adjust my window. -10 to 10 for x, probably still fine. If you want to make it a little smaller, like -6 to 6, because we only care about -3 to 3, that's good. The y values, though, we need to make much bigger. The y minimum, we know we're going to get to negative 46, so let's make it negative 50. And we know we're going to get to a maximum of 62, so let's make it 70. And just to make it scaled look a little bit, I'm going to make the scale 10. But if you graph this, then you can trace or even find your maximum minimum and see that it agrees, but we can just estimate it. Look up here. Oh, actually, it's perfect. We traced over and see that we have a maximum at x is negative 3 and y is 62. We see that there is a minimum. I can't believe it worked out perfectly. At x equals 3 and y equals negative 46. If you trace and don't get exact these numbers, just seeing that they're close really confirms that you did it right. And you can also see we are increasing to the left, decreasing in the middle, and increasing to the right. So everything we did worked out perfectly. Now, if you were to accidentally plug in the x values into the derivative to get the y coordinates, you'll always get 0 because that's how they were made. So that would be probably a pretty good indication you plugged it into the incorrect one. Now, the last one's super easy for doing this, because the thing to figure out the maximums and minimums, we need the critical numbers. If you remember, this function had no critical numbers. So this is just D and E, or there is no extrema. Right, that negative 7, if you remember from before, that negative 7 was the partition number, but not a critical number. The fact that it's going from decreasing to decreasing, so it's the same, isn't as important as the fact that it is not a critical number. Right? So if we had this problem set up the same exact way with no critical numbers, but this went from decreasing to increasing, it would still be D and E because there are no critical numbers. But you can graph this and kind of explain the difference here. So the critical numbers you can see actually on the graph. Now if we graph 1 divided by x plus 7 was our function. Remember, the critical numbers aren't in the domain, so we're just going to hit zoom 6. And you can see what happens here at negative 7. That's where we have a vertical asymptote. It's not actually on the graph. Since it's not actually on the graph, it can't be a maximum or minimum. So that's why we have a requirement that it must be in the domain. But for this section, if you get this section down, the next section is very similar, which you'll see. But really get this section down, and then the next section will be relatively easy.